Okay, well, here we are at the closure of the inaugural Keith Parsons project. Sorry, the simple puns are the most satisfying, and I've been waiting to say that all week. I'm just so glad no one else got to it. So I thought I'd stand up here and talk about something I know and understand, and then I thought, why the heck should I? That's a joke. I've never done that before. And a couple of weeks ago, I got a bit excited about this, and I sent around an email to my friends and colleagues and said, not only do I have nothing to wear this thing, I have nothing to talk about. And that was a bit of a problem. But what we came up with was a couple of things that have been bugging us as a company for the past 12 to 18 months. They're not really mainstream yet. They're quite different from most of the things we've looked at this week, but I hope you'll find it interesting. And I hope you'll find, as you go forward over the next 12, 18 months, that you start to see these ideas and concepts coming through in your work and the customers you visit. So things usually come in threes. I think David Sheraton said that if you've got four, you've made it too complicated, and if you've only got two, you forgot one. So I made everything fit into three. But I'm going to talk about really two things here, as you'll find out. The first one's IPv6. So I'm hoping that people will at least learn a little bit that you didn't know before about IPv6 and wireless here. So let's have a look. About maybe 18 months ago, we found that the larger Silicon Valley companies, tech companies, were starting to push IPv6. We've since found a few universities, especially larger ones, doing it. And the next part of the presentation is really just talking you through a storyline of how we stumbled along and ended up with something that we think is successful in terms of accommodating IPv6. Often the way things happen, isn't it? And I'm going to take aim here at our old friend, the VLAN. Been with us for a long, long time. Our conclusion is that its time has come. And I don't hope to convince you all today, but I hope to plant a couple of seeds in your mind that over the next year or two may come through and convince you that there are better ways to build networks. And the interesting thing here is it's the WLAN that starts to push these better ways to build networks. So I'm not going to go through all the bullets here, but we know that we have VLANs. We know that we've come to use them for different things, which you could certainly argue they weren't intended for. That's not particular news. We also know that there are various things that are not ideal about working with these critters. And I think most people would agree with most of these points. So, how do we get there? Well, the story starts with a very large high-tech company in Silicon Valley starting to do IPv6. And to look at this part of IPv6, we need to learn a little bit about Slack. Now, I'm sure some of you know a heck of a lot more than I do about Slack, so I'm going to talk fast and not take any questions. And that way, you'll get my view of things. Come put me straight afterwards. So if we look on this diagram, the first thing that happens is that a client pops up on the network, figures it needs an address, and it has to go and ask. And it asks using this stateless protocol. Stateless. So it asks by addressing an RS, which is a router solicitation, to the router on that subnet. It goes up. What color have I made it here? That's the gray stuff. So it goes up through the network, it gets to a router, the router sends back generally a multicast router advertisement, an RA, and that'll come back, and the RA has effectively the first half of an address. So that's the first half of it, which identifies really the router, the net. And then the idea is that the client adds something pretty close to its MAC address on the right-hand side, and that's how it makes an IPv6 address. So you can see this is pretty different from DHCP. We can use DHCP and IPv6. Our customers generally have chosen not to. They're using Slack like this. So that's how things should work, and I've put up a lot of stuff on this slide, and I apologize for my small fonts, but I like to get a lot of stuff on a slide. For one thing, it means you can look at the slide and you don't have to look over here. All right. What's wrong with that? Well, nothing's wrong with that until you start looking at that multicast coming back into the wireless part of the network. And that multicast transmission from the router in blue here comes down to the access point, and it goes out. And because we don't have a way of doing multicast groups in Wi-Fi, everybody under that network, under that access point, hears it. And I've drawn two little clients here in my usual blob format, and they're both getting the same router stub there. They're both getting the same RA from the router. And that would all work really well if it were not for mixing VLANs on access points. So here I've drawn different colored VLANs, different colored clients belonging to different VLANs, and some access points you have homogeneous, you have all the clients on the same VLAN, and other ones you got mixes. Where would you get mixes? You'll get it from our wonderful feature, VLAN pooling, which, as I've put in here a couple of times, is actually a pretty useful feature. A lot of people like it a lot, but it does cause this. I mean, it causes it deliberately, doesn't it? And you'll get it for other reasons. You'll get it from mobility events. You'll get it if things are supposed to pick up for different services and so on. So we get mixed VLAN clients on an access point. And what happens when we mix this with IPv6 and Slack is that different clients will hear RAs from different routers, because these things are coming out periodically or near periodically, as well as from solicitation from other devices elsewhere on the VLAN that may be on different APs. And they all come down here and they all go broadcast. And so what you'll find is that the clients will build multiple IPv6 addresses, which they're supposed to, but they'll be built on different VLAN stubs. And the problem comes when the devices don't figure out which one they're supposed to use. And as I say, this is all a true story. We learned this as we went along a little while ago now, but I think we figure we understand it now. So you end up with this mix of addresses, and the problem that pops up is that the fellow on the left here is using his blue address. He's supposed to be on the blue VLAN, and everything is going to go very nicely for him. The fellow on the right should be on the purple VLAN, got his address, or one of his addresses, from the blue VLAN and tried using that. And the first thing that happens is it hits the edge of the network, in this case, the AP controller combination, and it gets dropped. Gets black holed, because there's this nice little security feature that says you're not supposed to go spoofing, and we know that this fellow's on the blue VLAN, so he shouldn't be using an address which is associated with a purple one. Boom. And this happens in a statistical manner. It doesn't happen every time to every client, and it pops up every here and there. So you can imagine that it took a little while to track down what was going on in the network. But that was our problem in IPv6 with Slack. So what to do about it? Well, the first thing we did was say, aha, we'll change the multicast to unicast, because wireless people like doing that. We figured out how to do it with video a little while ago, and it's a neat trick to play. So as soon as you turn it to unicast, now you can make sure you hit the right target, generally. But you're still going to get quite a lot of traffic coming through, because every time someone sends an RS, or there's one of these periodic RAs, there's an RA that comes through, and you send it through to your client. And we discovered that that actually caused battery life problems. There were, and I'm always a bit skeptical of user reports, but in this case they were absolutely right. There were reports that when we're at work, the battery is going down much faster than it used to, and when we go home, it doesn't go down that fast either. So, there was something wrong, and we figure out it's probably this mechanism here. And the mechanism is that when you've got multicast coming from your AP in that top diagram, the client only has to wake up for the DTIM, figure out there's something there, and then very soon after the DTIM, he's going to stay awake. Very soon after the DTIM, he's going to get the multicast packet, and then he can put his radio to sleep. So he's in receive mode all the time, and not for very long. If you look at the bottom diagram, what happens when there's a unicast to pick up? First of all, it takes a bit longer, because first the AP does its beacon, the DTIM, then it does the multicast stuff, and then there's a bit of contention, and then eventually you can send your packet up and say, give me my unicast. And so it takes a bit longer, and then there's that packet going up, and then the ACK, and then there's the going to sleep again packet. So there's a couple more transmits in the chain. And we found that this actually ended up being quite apparently a significant effect. So what can you do about all that? You get to the end of it. We got a question? Chris? Wouldn't the multicast to unicast apply to IPv4?
Use more battery in IPv4 as well, in that same mechanism?
If that's exactly what's going on, then I would have expected a similar effect in IPv4. I haven't noticed that before, and I'm not sure I've done good enough experiments to figure it out. So there may be other stuff going on here. One of the things that we also figure out is that in IPv6, there's this duplicate address discovery, DAD. It's all part of the same RFCs, and that involves quite a bit of back and forth. So initially, when you're setting up a linked local address in IPv6, you're supposed to test it and make sure that it is unique, and there's nothing else out there using the same address. And then when you get your stub and you form your address in part of Slack, you're supposed to do DAD again and make sure that it's a unique address before you start transmitting. So the extra overhead of all that stuff may be significant as well. So what can we do about it? I'm not going to answer all the questions here, but there are obviously a couple of things you can do. Some people look at that and say, aha, well, what we really need is to extend the whole VLAN model into the wireless. And you can do that. And people have done it by using different group keys to separate traffic. We looked at that, and we figured we probably don't want to go that direction, but we'd like to go another direction, which we'll get to later, and make the VLANs bigger and make this mix of different VLANs on the same AP happen much less frequently, hopefully not at all. So this industry being a wonderful, open, and competitive industry, you'll see people going about this different ways. But I wanted to introduce those ideas in IPv6. All right, I'm going to move on to a couple of other things here. Consumer devices is not such a new thing. You've all seen this probably before in different ways, but I've got perhaps a slightly different slant on it. So as we're aware, things came out of the consumer market with a single AP model, and they end up appearing on our networks. I'm going to talk about our friends MDNS, Rendezvous Bonjour, and MDNS is on Android now, of course. So this is what it looks like in my terms, anyway. What we have is a multicast means of maintaining distributed databases of service instances. And services are identified by type and instance. If you're in iOS, they've got a very nice package where it's all done in the OS for you, and all you have to do in the app is ask, where do I find this? And it's already cached. If you're on Android, you have to build it yourself, and then you have to figure out how to get around the Android bugs, which hopefully are going to be gone soon. But you can do essentially the same thing. So we have an advertisement when a service comes up. We have a query when you want to know what's going on. If you're on Android, that may get trapped in the OS and not go out. And then you get responses that come from the service type that you've asked for generally. There's a lot of multicast in this, obviously, because it's supposed to work in that sort of format. And you end up with this, and we're all familiar with this. I'm not going to go into all the details that I might to a different audience. But essentially, you end up being trapped in the VLAN paradigm again. We've got this thing that we build for various purposes, and now we find that we drop these consumer devices into it, and we have trouble because everything hears everything within, but then it doesn't hear anything across from different ones. It's the solution here that I think is quite interesting, and the solution is not necessarily to join the multicast links together in different ways. It's to drop what in SIP terms we would call a back-to-back user agent into the network. So everything that comes from a client as multicast just gets intercepted and terminated right there. There is no propagation of this traffic as multicast. If a response is required, then either the network goes around and sends out a multicast to what it considers interested parties, pulls the responses, and then tells the original requester what it should get. Or it just gives an immediate response, a bit like that iOS operating system in the previous slide. So now your network is becoming pretty intrusive. I don't know if anyone else is as scared looking at this as I am, because if you make a mistake, it's not a good thing. But it seems to be out there, and it seems to be successful enough that I'm not quite as scared as I was 12 months ago. So that means you can end up with different views of the network defined by what devices can see on multicast, but entirely synthesized by the network. And that's really my point in this little section. So at that point, the network has figured out how to do the two different functions that we're looking at on the bottom. The connection within the network on the left and between networks on the right. And do it dynamically and do it somewhat intelligently. I want to point out that this isn't necessarily something completely new. There's been Proxy Up around for quite a long time in the Wi-Fi world. Now, again, there are different ways of doing Proxy Up. The simple way is just to say, I don't want a lot of multicast to be going out over my Wi-Fi over the air. So I'm just going to stop things at the AP and have the AP respond back into the network. But you can also apply that paradigm we looked at in the previous slide to Proxy Up, and indeed, that's done. So now the network's figuring out what gets to see and what doesn't get to see the other devices in the network. 11v has already got multicast filtering built into it, which in a way is the other side of the same structure. So when we start doing SLAC and IPv6, we're really using the same forms that we've used before, but extending them to new protocols. So let's try the Beehive picture. What I'm trying to point out here is that the network is doing a heck of a lot more than it ever used to do. And the bottom layer here is like a traffic forwarding layer. So this is where things move back and forth, but it's got an awful lot of switches in it. And it can create packets in response to things that are coming from the clients. And the way it knows how to do all that is from a slightly abstracted layer further up, which I call some sort of policy layer, which is where you put in the rules. And this is where you put in the rules to say, this particular device can see these screens and can show things on these displays. Or if I'm here, I want to see these particular printers. And you've all seen the sort of rules that we can apply to that. You can apply geographic rules, you can apply ownership rules, things like that. But if you think about what's going on in the network, there's the policy layer, and then there's an implementation layer going on there further down. I've got a slide here about migration to the cloud, but I haven't a clue what I ought to be saying about that, so I'm not going to do that. Someone can tell me afterwards what we should add to this when we do it for real. But I thought I ought to wave my hands and say cloud. The only thing I have so far is that the AP, if you've got a corporate AP out somewhere at a remote location where there's an employee or whatever working into the cloud, that corporate AP is about the only touch point you have. It's pretty tough to troubleshoot down to the device. It's pretty tough, at least in my limited experience, to troubleshoot in the Amazon Web Cloud, at least for connectivity questions. But if you can get to that AP, you can figure out what's going on. You can put in some policy rules. Again, you might not often want to do that, but if you've got limited bandwidth, you can certainly put in prioritization rules and maybe some routing rules and things like that. So somewhere there's a theme of unification, and I haven't quite finished it off. So when we look at these things, what I hope I brought together with these rather different stories is that we're building new features in response to customer problems and what we see at the customer, and generally what we stumble over the first time we see it. But what has happened as a result of those things that I've talked about is that we've developed a fairly strong structure where the network now intercepts at least most of the multicast protocols and synthesizes responses and puts itself in the middle there. And that's something that will, I'm sure, be built upon over the next few years. When we return to our friend the VLAN, which I came in with, I think if you put together things that I've talked about so far, I think we can start to make a case that the network can do pretty much everything we have done with VLANs in the past. And then I'd wave my hands and say the other ones are irrelevant anyway. But no. The reasons that we have VLAN segregation today are generally reasons that are no longer valid. I would argue that a lot of places we have VLANs, it's because we built it 5 years ago or longer, and we don't have the time to go back and re-engineer it. IPv6 is an opportunity to re-engineer it. A lot of people, when they come along with IPv6, for one thing, they have budget, and they can have a team and a project. And I think that's a real opportunity for those of us who get to talk to these people to say, hey, why don't we think about the VLAN and about whether you're going to need it in an IPv6 network? And there are a couple of ways to look at this. You can either do it as an overlay, so your IPv4 network stays the way it is with VLANs, and you build an IPv6 network on the top, but just for IPv6, you make it big and flat. Or you can try and move everything together. And I've talked to different people in my company, and I've had different opinions. You know, one opinion is you don't want to have a mental model of two types of network in your head. You'd much rather troubleshoot with one. So that's the argument for doing it all together. And then the other argument says, well, let's not re-engineer something that's been out there for a long time and is working tolerably. Let's put it into the new part of the network that we're building. I don't think we know the answer to that yet, but the opportunities exist. All right, the last part here is taking those concepts and pushing a little bit into something else that we've been talking about for a couple of years, and that's SDN. SDN obviously is much more prevalent in the data center, where I believe it really got traction because it gets you past the VLAN limitations, which is somewhat ironic. But I'm sure you're familiar here with the architecture of SDN. Abstracting that control layer from the network, being able to give it policy, and then having it implement that policy down in the bits, well, the parts that move the bits. And of course, in the reverse direction. And I asked one of my colleagues who knows a lot about this, where is SDN in the enterprise today? And he said, well, mostly used in hospitals for audit trail. That upwards flow of information for audit and logging. It can do a lot more than that, and we should be thinking about these principles and structures. So when we apply that SDN model and compare and contrast it to what we came up with a little bit earlier, you can see that the network part at the bottom can be used to move bits around, to change connectivity, to change topologies on the fly, under control of that next layer up, the policy layer. And the policy layer itself can be influenced by external APIs, which by another term you could call SDN. You can think of your Palo Alto firewall that Chris was talking about earlier, integrating. You can think of a link server where it can provide the network with some information that there's a connection going to be made, and then the network can figure out, oh, I need to move my client from one AP to another AP to get better load balancing, or to give it a higher data rate so it can support the video call, anything like that. So we'll see more of that. Just a couple of slides here to point out that the edge of the network is the only place you can really do this. As you get further from the edge, you get less and less visibility of stuff that turns out to be quite important. And I won't belabor all the things I put on the bottom of the slide in small print, but there's no doubt that the edge of the network, where you see everything that happens all the way from the wireless up to the protocol level, is a very important place, and it is a place where you want to sense and then forward that information up to these policy entities higher up in the network. And then, of course, those policy entities can tell you what to do. So now you have a network that will reconfigure itself under control of those policy entities. And again, you need to be back to the edge to do that part. You can't do that when you're further back in the network because you've lost the wireless interface, for instance. So there we have a new sort of model for the network, which is much more in the SDN structure. We have policy from the top, which is taking input either from the traffic going around the network or from external entities. It's then providing some policy and control information down into the network, which then reconfigures it to do whatever is required. And we'll see. I think that may be a model that we'll start to see over the next couple of years here, because certainly all the parts are in place to do that. So there we are. The network will hollow out. We will get larger VLANs, fewer VLANs, hopefully. We'll get rid of VLANs, perhaps. And we'll get policy-driven network out of all these building blocks that we put together earlier. Thank you. Take questions, of course. Any questions?
You mentioned the whole VLAN paradigm and should it be reduced? And I guess I answered that question. Looking at that question is, well, does IPv6 reduce broadcast traffic?
Sorry, the question was IPv6 is?
Does IPv6 reduce broadcast traffic on 802.11?
So the question was, does IPv6 reduce broadcast traffic on 802.11? Not intrinsically, but the mechanisms I showed you that have been developed for other purposes are used to do that, and then you've solved that problem, yes. So therefore, my argument here was that therefore you shouldn't be worried about the broadcast multicast traffic. We have some skeptical customers right now. We have some customers who have absolutely done it and are doing it on large networks and seem to be pretty happy.
It seems like a lot of work to just not use DHCP6.
It's a lot of work to...
I mean, the idea of I've got to segregate multicast domains for VLANs seems like a lot of work just to avoid using DHCP6 versus trying to do an IPv6 overlay to my IPv4 or things like that. To me, it's like, why not just use DHCP6? You solve 90% of that problem, and the VLAN problem will go away once we get rid of IPv4 at some point after we're long gone. So.
Okay. I think there is an argument here that you're taking complexity from one place and putting it in another. There's an argument that says this is not a big enough problem that people need to deal with it, that people need to change things today, which is disruptive and manpower intensive. I'm probably not equipped to go into all those arguments, but I do want to observe that we have a number of customers who absolutely are picking up their stuff and doing what I explained here, which is one reason I brought it up, because I thought it's an interesting thing to see.
When you're talking about flat networks, how big are you talking?
Flat networks.
When you say no VLANs, how big are you talking?
We're not on film, are we? One of the big CSUs, Cal State Universities, has done this. And
How many devices?
Tens of thousands. Not many tens of thousands, but tens of thousands. Yeah.
Well, thank you very much.
Thank you.